Hello, everyone. How are you doing this morning, this evening, this afternoon, wherever you are? My name is Jay Metz. I am going to be your host and MC for today's SNIA Networking Storage Forum webinar. Today, we're going to be talking about how some of the hyperscalers leverage NVMe cloud storage. In particular, we've got our friends from Facebook and Microsoft coming in to help us understand some of these things. One of the things that's been very interesting in the industry and in the trends has been the fact that people have been looking to companies like Facebook and Microsoft to get some guidance as to how to use the technology in new and interesting ways. So that's what we're going to be focusing on today. So as I said, my name is Jay. I am a member of the board of directors for SNIA and also on the Networking Storage Forum. And I will be your host and your MC today. I am joined by Ross Stenford from Facebook and Lee Pruitt from Microsoft. Hello, Ross. Hello, Lee. Welcome.
Thank you very much. Welcome, everybody.
So what we're going to be doing a little bit to start off with is give a little bit of administrative trivia to help you out and understand who is doing the presentation and what we are all about. Yes, this is the advertisement for the sponsor. You can cope with it like everybody else. Welcome to SNIA. If you're not familiar with SNIA, we are one of the world's leading storage industry organizations. We've got over 2,000 active contributing members and well over 50,000 professionals worldwide. And we have a great deal of work in terms of specification standards as well as a variety of different storage topics. Amongst those topics, we have this, in the networking storage forum, we focus entirely on the networking part of storage for SNIA. Our group within SNIA focuses on anything that has to do with being able to transport different storage technologies, including the new and interesting stuff like NVMe over fabrics. So if there's additional technologies that you would like us to cover in any of the webinars, please feel free to let us know, and we will do that as time permits and as we can find the appropriate experts to give vendor-neutral and technology-neutral webinars to help you understand the basics as well as some of the advanced information of how technology works. Excuse me. Now, before we get too far into it, I do have a little bit of administrative trivia that I'd like to try to share with you, not the least of which is that, just so you know, this is a copyright presentation by SNIA unless otherwise noted. Anybody who is a member company or individual members can use this material as long as the slides are not modified and SNIA is acknowledged as the source. Just be aware that these presentations are without warranty, express or implied. You can use at your own risk. You can get a copy of this underneath your console. You may see a button that says, or a tab that says attachments, where we do have this particular presentation available to you. We will also be providing this at the SNIA.org website afterwards. Just so you know, there are a couple of other things that are useful to understand, and then I'll be done, I promise. If you wind up having issues with your audio, one of the things that we have found is that there could be some issues with caching in your browser. So if you've got a lot of tabs open or if you've got YouTube running in the background, you may have to wind up clearing your cache to get a smooth and consistent audio for the presentation. Other than that, I do want to tell you in advance that we really need and look forward to your feedback. Good, bad, ugly, indifferent, whatever it is, we do appreciate the effort. Our speakers spend a lot of time trying to provide you with the best information that they're capable of, and this is the only way that we know whether or not we're actually achieving our goals. So please make sure that you leave some appropriate feedback for speakers as well as for us at SNIA. Having said that, if you've got additional questions, you'll notice that there is a tab at the bottom of your console that allows you to ask questions to the speakers, and you can feel free to do this. I will be the moderator for those questions as they come in, and if we don't have time to answer the questions, please don't feel bad that we couldn't get to them. We will be providing a Q&A blog at the end of the presentation or after the presentation. Give us about a week or two to put it together, where we will put all the questions that come in into the blog that are appropriate. And I think there are people on the call who know who you are. Appropriate questions only, please. And we'll go ahead and answer those in a block. Now, having said all that, I have wasted enough time for the 5 minutes of this trivia, and I would love to hand it over to Ross. Ross, my friend, you are up in NVMe in the real world. This is all you.
Thank you, Jay. So NVMe in the real world. Let's get to the excitement here. So Facebook's mission is to give people the power to build community and bring the world closer together. That's our mission, and that's our goal. And now let's talk about things a little bit. Today, Facebook has grown to over 2.7 billion people, 1 billion people using Instagram, and 1.3 billion people actively using Messenger. All told, over 2.5 billion people use one of the Facebook products every month. While growth of new users and content is continuing, our infrastructure has to keep up. In the background, you see one aisle from one of our data center halls, which now numbers in the double digits. The data centers are filled with servers, storage, and to support all this data, we use Flash to provide the optimal experience for everyone as possible. As you can see, this much hardware is a challenge. Now, let's take a look at an aerial view of our data centers. To give you a sense of scale, this is like 4 football fields in length. Our data centers are large warehouse-style buildings that house the storage, compute, and networking equipment needed to run the Facebook family of services. You'll notice that many of these are shaped like an H, the 4 data hall wings and an office area in the middle of the H. This is a common design, and it's useful so we don't need to redesign our data centers each time we scale.
So, switching it over, talk a little bit about Azure at scale. We have over 2 million miles of data fiber running around the world to connect up our 54 Azure regions with over 100 data centers. And of course, as you can think about all those data centers, there's millions and millions of servers in them. And so we're able to serve about 72 plus terabits per second on our backbones across the world to all of the customers that use Azure, either the services or product as a service, infrastructure as a service. Bing runs on Azure and many other services as well. And so, why NVMe? So NVMe, because the needs for our data centers are growing pretty much exponentially. You can see the nearline exabytes trend here from the Trend Focus research going forward from now into 2023. It's just hockey sticking up. And so with that, we need to be able to take that data and store that properly, make sure that it goes back to the user when they ask for it, it's not corrupted, and that it comes back quickly. So we have certain SLAs that we need to ensure to those customers, and so NAND Flash is part of that SLA structure. And with that, NVMe is the best placed interface to do that at scale with good performance. So, Ross?
So Lee, I completely agree with you on NVMe. Let me show you a graph here where we have, on the left side, we have IOPS per terabyte. On the bottom, we have system flash capacity. And our need is for performance to scale per terabyte linearly. So if you have a 1 terabyte and then you go to 4 terabytes, you need 4x the performance. So it all scales linearly. As you can see here, the NVMe line, I'm able to scale the IOPS per terabyte so they stay the same as I increase the capacity. Whereas with SATA drives, the performance drops off. This is the reason I need to use NVMe today, and why we're aligned to NVMe is because of this performance. Now I'll pass it back to you, Lee.
Oh, yeah. So we're just going to talk about, there's a few things we want to talk about, issues at scale. around all of this stuff that we're storing and how we get it back and forth and give it to customers and keep it for them and all of that. And so we want to talk around certain aspects of storage and how we manage that storage, especially at very large scale. So things around De-Allocate, which is basically the trim function in SSDs. We want to talk about remote debugging, all the stuff around how do we find out what's happening with all those devices, millions and millions of them across the world, and make sure that they're all functioning properly, and if not, what do we do about it? Of course, one of the big things nowadays, security. You know, that's a hot topic everywhere. One of the things that we're going to need to talk, about in the future is how do we ensure that these devices have the firmware on them that we expect, they're doing what we expect, and they haven't been compromised. Also, we're going to talk about rot in place, which is kind of the idea of, hey, given these millions and millions of things across the world, how can we ensure that the useful lifetime of them is as long as possible, and as things degrade, they degrade gracefully and don't fall off a cliff. And lastly, we want to talk about some stuff around form factors. There's new and interesting ones that have come out for the data center. We want to go through some of the aspects of those and why we feel that they're important. And then we've got a little bit of a teaser of what's new going on into the future. So with that.
Sure.
Ross?
Let's talk about NVMe De-Allocate, the challenges and improvements. So the goal is it's a hint from the system to the SSD that the system no longer is tracking certain LBAs. And that's great. It reduces write amp, it improves performance, endurance. Life's great, except there's a problem. This can cause latency spikes due to the de-allocation with the blocks, reads, and writes, and impacting performance. And we all want things now. Nobody wants that. So the old solution was you tune your system based on de-allocate size, and that's really challenging because which supplier do you tune for? Because they all have different sizes they want. They work better and worse, and tuning the system across a bunch of suppliers is very painful. So NVMe 1.4 now has a new solution. Now the SSD can advertise to the system its preferred de-allocate size. And this allows the system to be optimized using standard mechanisms that scale. Next, let's talk about managing at scale. This is a challenge. With the more hardware you have, the harder it is, the more challenging it is. So hyperscale requires debug with no physical access to the SSD. So the first challenge is there's restricted access for vendor-unique tools. There are no vendor-unique tools, and so how do you deal with this? And there is a tool called NVMe CLI. It's open sourced, has active industry contributions and updates, and it takes a vendor-unique plugin that pulls and reports the logs in a common format such that all the drives now appear the same. So this allows for remote debug. But now the next challenge with debug is, okay, I can debug my drive, but how do I get the information I need to resolve the issue? I know something's wrong, but what is it? The solution here is telemetry. This allows SSD providers to get the remote access debug information they need to resolve their issues and allow them to put different data in different areas for different levels of debugging. And this provides a path forward so problems can be solved and life can get better.
All right.
Lee.
So from the Microsoft side, and so when I walk through some of these things, you can think of remote debugging in the sense of, well, it might be kind of hard to go on site to access that server and that device that might be having an issue that we can't figure out what's going on because that data center may be sunk in the ocean. So you've got the little picture here showing some concepts of taking a container-sized module, packing it full of servers, putting dry nitrogen in it and putting it in the ocean, and that's how you cool it and it just sits there for the lifetime of that sole module, which could be 5 to 7 years. And so how do we get to the data on these things to ensure that if there's a problem, we can figure out what it is with the supplier, with the SSD vendor, figure out what's going wrong, and then develop a firmware that we can then update that device remotely. So some of these things that we use, that we need from the device that help us to find some of these issues are the NVMe timestamp feature. So this is a feature where at boot time or when the device is reset, the system actually, the host software sends a timestamp command to the drive, giving it the wall clock time. And with that wall clock time then on the device, as events happen inside the device, they can be marked with that wall clock time. And with that, then when we get that data back from the drive, from those events, we can now correlate it with what was happening on the system at the exact same time, such that we can look back and forth for indicators of problems on either the host side or the device side. Now, as Ross described, telemetry is a very important part of this equation as well. The telemetry command from NVMe is set such that it can also be host initiated, in the sense that I can go from the host and I say, oh, drive seems to be something's happening with this drive. Maybe I'll go grab some telemetry from it and get it back to the vendor so they can tell me if there was something going on with it. Also, of course, the drive, and many times a drive will know that, hey, I have a problem with myself. Something's going on here that might be interesting. Why don't I tell the host that now would be a great time to collect telemetry from me because I've got some stuff to tell that went wrong inside. And so things like that, a firmware panic or something wrong with the firmware flow or something that's odd with the NAND itself, something like that. And another important aspect, smart data. So this is both the standard smart data that's defined in NVMe and also some specific smart data that we ask for from our vendors as well beyond that. We'll talk more about that at the end of the presentation. But around this, that we collect this data from all the devices in our data centers, millions and millions. We collect smart data every hour. And so with that, we can start to do things like machine learning, trying to understand if a drive is starting to die, what we have to do about that, whether we need to take it offline, reformat it, help it in some way, or whether it needs to be replaced. And so with that, obviously all that data is available. So we can say basically to the SSD IHVs, how many terabytes would you like to see and on how often? You want to see that every week, every month? We can get that to you and help you understand what's happening with your devices at scale. Now, with that does come a caveat. Any of the data that leaves our data centers must be human readable. So I need a decoder ring to say that if that telemetry data has stuff in it, what that is, so we can ensure that there is not any personally identifiable information with that, because my security guys are extremely paranoid, and so we have to follow the guidelines that happen around that. All right. So with that, next slide. On to Russ.
Sure. Let's talk about some of our managing at scale problems. As things get bigger, there are always challenges. So let's give some background here first. So the amount of data written to an SSD might exceed the endurance of that SSD in its lifetime. And given some amount of fixed write bandwidth, a low capacity SSD will wear out faster than a high capacity SSD. Examples of this where applications can occur are logging and caching. There are lots of ways where this can happen. So let's talk about a real-world example of this challenge. So we have an application that only needs 250 gigabytes of flash, but it'll use all the SSD capacity. Very well-written application, scales very well. But the application write rate is high enough that it'll wear out the 256 gigabyte SSD. And consequently, how do we get an SSD with more endurance that will work for this problem? And because the application write rate scales per terabyte, so if I go to a higher capacity drive, it'll continue to write at the same write rate, and it'll continue to wear it out. And so we're in this repeating cycle of non-convergence with an application wearing out a drive. So how can we go about solving this problem? Well, fortunately, our friends at NVMe Express came up with namespace management. And namespace management allows us to take a 512 gigabyte SSD, configure it as a 256 gigabyte SSD, which then effectively doubles the endurance of the 256 gigabyte SSD. Thus now the application view is 256 gigabytes with double endurance. So this scales very nicely for a simple method of creating more endurance on a drive without creating customization or other challenges. Next challenge we'll talk about. So how many blocks on my SSD have data and how many do not? If I run a bunch of stuff, I deallocate a bunch of blocks, how many blocks really contain data? What's my effective over-provisioning? What is this from a performance point of view? I know I did a bunch of stuff and got some result, but how many LBAs actually contain data? And that's where namespace utilization comes in. This allows the user to determine the number of LBAs that actually contain data versus trimmed in some fact. So now you can figure out what your effective over-provisioning is. So it's a very convenient method. So now let's talk about some challenges. We all know that security challenges are growing. They'll continue to get harder. And NVMe Express supports security send, it supports security received. We can tunnel security protocols into an SSD. That all works great. There's even an open source tool for Opal security. You can go look at that. It works very well. That's all great. However, unfortunately, there are also challenges. Secure boot is a common security requirement. This is a process that ensures that the firmware running on the device is from the manufacturer, not from some other source. We want to be sure that we protect user data, and part of that is making sure that the firmware on the device running is what we all think it is. So everything is protected, it works the way it should work. And many people implement it. It's a very, very common security feature. The problem is there's no standard way to know if secure boot failed. If the firmware on the device is compromised, how do you know this versus any other type of failure? Maybe the drive bricked to a firmware problem, or a regulator issue, or some other issue. How do you know if it didn't come up if it is a secure boot failure or some other failure? This is something as an industry we need to come up with a standard way of identifying, and so that everybody uses the same mechanisms, and us all doing the same thing together make the world a much better place.
All right. So security, again, from our side, obviously, Azure data centers and Windows in general, security is ultra important. We need to ensure that our customers' data does not get hacked in any way, whether that be from sort of things like malware or other things like state-supported actors, and especially in the face of things like the JEDI contract, where we'll be actually storing data from the government itself. We need to ensure that that data is safe. And so with that, one of the mechanisms that we use is what is called eDrive on Windows. That's our moniker for what is Opal v2 plus the IEEE 1667 security silo. So in conjunction, those two operate together in a Windows environment to work with BitLocker as the key manager to manage keys on the device that then encrypt different regions of that device to a different key and allow for the hardware on the drive to actually do the encryption support. Now, as I said before, my security guys are quite paranoid, and so we actually do double encryption. So the encryption is also done in the storage stack itself. When you're storing your stuff from your VMs onto our storage devices, it's encrypted both in software and, as I say here, through eDrive. It's also encrypted on the hard drive itself. And some of the things that Ross touched on the hardware root of trust. So that's walking through secure boot. Does the device have a secure world on it such that it's measuring the boot process inside itself as it comes up? Ensuring that the firmware is assigned firmware that belongs with that drive, and it's there and ready to go. And something that we have added, Cerberus, is our security chip that we put on our motherboards. Google has their Titan chip that they're open sourcing, that sort of thing. But this is basically a piece of hardware that goes on the motherboard itself that looks out and attests that the firmware on every piece of hardware on that server motherboard is the firmware that we expect and is the one that we want to run before that device is allowed to come out of reset. And so that way we can ensure that all those different pieces, like there's no issues with the supply chain, there's no issues with hacks or anything like that, especially in the face of where we have the infrastructure as a service support where we give some servers to bare metal. They get the full access. There's no hypervisor in the way, so there's no real way to guard that server from somebody's malintent other than having something like Cerberus on the motherboard itself to ensure that the firmwares aren't being changed when we don't expect them to. And so kind of another facet of this is actually something that we're pushing on the IHVs for is around device hardening. So this would be things like requirements for pen and fuzz testing of the device. And you'd think, well, it's like, well, hey, well, how can the device, why would you be able to do something with a device like that? Isn't this more for a software concept? Well, you can think of all the lines of firmware inside that device. If there's a coding error in there that somebody can do something through the protocol, they can, send malformed commands to the drive. And if the drive firmware isn't hardened against these sort of things, bad things can happen that somebody can exploit. So around that, this is something that came up not too long ago, was in the news about a year ago, where people were able to hack into devices because people left debug ports open. So one of the things that we require through our process is the locking down of these things. So either they need to be turned off at the factory or put behind some sort of a crypto system so that debugging can't happen through either a JTAG port or a serial port or even through things like vendor unique commands that we may not know of because the device, they're vendor unique. So these are all the things, some of these aspects around how we ensure that devices can't get compromised inside our data centers. So next one here we want to talk a little bit about is what we call rot in place. Again, showing the picture of our concept of these things down under the water in the ocean. Obviously, it's a little hard to put a tech in a wetsuit and go through some sort of chamber to go inside one of the things to service an SSD. And so around that, we want to ensure that we can have a device. It may not be an optimal device, but the device can keep going along through an extended service lifetime. And so what we're looking for around these is a 5 to 7 year device service life. And so some of the things that we want to be able to do with that is basically know the endurance rating of the drive, i.e. how many petabytes can I write to this drive as we go along. And what I want to be able to do is look at the smart counter wear indicator, knowing that petabyte total, looking at that wear indicator, and basically heating and cooling the data. You can think of it as riding that line of endurance wear down by heating and cooling that data as we go over whatever service lifetime we expect from that drive. And then zone namespaces for QLC. I think I saw a question about, hey, what do we think of zone namespaces? we really like zone namespaces. We were one of the original authors of the zone namespaces FPAR in NVMe. The zone namespaces are kind of some concepts that came out of what we used to have for streams. Is another concept that we use earlier on from NVMe. Some people may understand the term Denali, which was a JDF that Microsoft drove to kind of make a more open channel type device. And I think with that, we were able to take a lot of the concepts of Denali and pull them into the zone namespaces and make that a broad industry initiative around that. And so with that, zone namespaces really helps with quad level cell for flash. The number of erase cycles on QLC is pretty low. And so, hey, again, going back to that 5 to 7 year lifetime, how do we ensure that we keep that device going for that amount of time? And so with that, zone namespaces, the sequential write, very large, great, very friendly to the flash, reduces the WAF almost to 1. Some of the other things that DNS is going to be able to give us is we can reduce the DRAM on the device, so we can reduce the cost because we'll use a much larger indirection unit, and not 4K or 8K, but something like 15 or 30K. And so with that, again, we're being the host friendly to that NAND media as much as possible. And with that, we can also, because we're kind of doing a directed placement of the data on the drive, we can greatly reduce the over-provisioning that a standard block device needs, and which would also minimize garbage collection because the host layer becomes responsible for that. All right. So, last item I want to touch on here before we get to some future stuff. One of the things that we're running into now in our data centers, our NVMe devices, currently we use the M.2 form factor, but it's a great form factor in the sense of it's a small, compact form factor that was available when we needed it, and we could take it, and because of its size and compactness, we could place it all over the motherboard in different spots where we could fit it, and we could outfit a server with up to 14 M.2 devices. But we found over the course of time, as the devices are getting larger and larger, the M.2 has certain power and thermal constraints. The PCB itself is somewhat fragile because of its thinness and the number of layers that it has to contain to route everything across that motherboard connector. As you can see from this, it's a little hard on the graphic here, but if you blow it up, once you get the presentation, you can kind of see here a VIA stack. And this happened to us in the data center a while back, where the VIA stack registration when the PCB was manufactured was slightly off. And it was just enough that the drive survived the power cycles during bring out factory testing, integration testing, and basically just as it went live in the data center, the VIA would burn out and the device would die. So this was not a good thing. And with that, also, M.2 is not hot swappable, so servicing can be an issue, especially if you have a system you want to try and keep running. So, what can we do about it? Some of you are familiar with the EDSFF Foundation has formed to take a look at the needs for data center scale device form factors. And with that, was we worked through that, and then once we had the set of devices that we were comfortable with, interested in, we donated that material to SNIA's SFF, where there's still work going on now. So if people are interested in that, please help out with that effort. There's a plug there for Jay. Sure wants me to do plugs for SNIA, so there we go.
Plug away.
So. But the good news is that all these form factors out there, they support NVMe too. So, kind of a
so Lee, let me just interject one comment here. Let me add, I completely agree with you. The E1S form factor is the form factor of the future that scales very well with NVMe.
Okay.
So with that, now that I hijacked your slide, you can continue.
Well, yeah, I guess that's a good point. Maybe we delve into that a little bit. And so you see here that I have both E1.L, which is the long version. Some people might know it as Ruler. That was kind of Intel's moniker a while back. And then E1.S is the short version. And you can think of this really, from our point of view, E1.L is great for capacity. And so we take these and we stuff a whole bunch of them into a JBOF, just a bunch of flash chassis, and put that up as bulk storage for our Azure storage folks. The E1.S, this is more interesting for our Azure compute folks, where we can have several of these, say 4 terabytes, 2 devices of 4 terabytes each. They go into a compute node, and they're then serve up what we call the ephemeral storage for all of the VMs that are running on that box. So, thank you. Thanks for bringing that up, Ross. Had a few more points there that I just don't make. So, you want to talk to this one, Ross?
Sure. So now, how about we talk about what's new in storage with Microsoft and Facebook? So with that, let's go to the next slide here. So Microsoft and Facebook are merging their SSD requirements into a single document. And let's talk about why are we doing this? So what's the problem? So hyperscaler providers have features that are needed to manage SSDs at scale, but not sharing these features with the rest of the industry. I was just on a call last night with somebody talking about their problems and how the drives they were getting and the drives we were getting were not the same and causing issues. There are many features in common across providers, but they each are implemented slightly different. Cloud consumers have confidential SSD specifications, but don't encourage industry collaboration and discussion. There's no public document on what a cloud SSD should be. The SSD industry is fragmented due to lots of different SKUs, everything's similar but different. I can ask for power to be measured one way. Microsoft can ask for power to be another way. We need to focus on things that add value and build the ecosystem in the community. In addition to that, there are third-party compliance suites. Well, what features do cloud providers care about? They don't know because the specs are not out there. So with that, Lee, let me pass it back to you here.
Okay. So as we kind of, at the top slide there is that we are taking, Ross and I have been working over the last 6 to 8 months. We've basically been either I've been going down there or he's been coming up here every couple of weeks, and we spend all day going through our successive documents and figuring out where the commonalities are. As Ross pointed out, there's a lot of data that we ask from the drive. I might want it in byte 3 of log page C0. He might want it from byte 7 of log page C1. But it's the same value. And so having those things be different, there's zero advantage for either Facebook, Microsoft, and the IHVs. It's just more work for them, more validation, with no representative differentiation available. And so we really want to get this doc, as we've been challenged by our management, to make this doc as 99% the same across us, with maybe some small addendums as there's certain things that just are different. But we want to then take this document and we're going to donate it to OCP as an open document that hopefully other cloud providers will also jump onto. Hopefully the IHV, the SSD vendors will jump onto as well. This has some great effects for everybody in the sense of many eyes on one thing. We can have that be the trunk firmware, and everybody gets all of the robust testing of the trunk firmware and across all the validations of all the different hyperscalers. And so it reduces market fragmentation, It simplifies things like the open source tools, and it allows third parties to really get in there and do validation at scale for everybody's benefits.
So quick jargon alert, you use the phrase IHVs, just for those who aren't working on this on a regular basis. What does IHV mean?
Independent hardware vendor. So that is basically the SSD makers. So.
Gotcha.
All right. And I guess we're on to everybody's favorite part of the...
That's right. Now
questions.
It's my turn. Whoa. All right, got lots and lots of questions, including a couple of doctoral dissertation questions for you guys. So let's see if I can put piece these together into some sort of coherent kind of a story. There's a lot of different questions about the nature of the NVMe protocol, as well as some of the specifics of different technologies. We cover quite a bit in this particular presentation. Some of the questions seem to come in around the time we were talking about encryption and security. So I'm going to go ahead and start there, and if we've got time, I'm going to kind of branch into some of the more generic kinds of questions. So one of the questions that came up was regarding how high of a priority is firmware malware. And, you know, from a hyperscale perspective, in particular, does this become something of an issue? And the question continues on, you know, are there automated and remote management methods for detecting firmware malware and fixing it at that scale, especially if you've got computers that are underneath the ocean?
Yeah. Ross, you want to?
Sure. I'll start, and then you can add to this if you want. So firmware malware is a huge issue. This is exactly why there's secure boot, is to ensure that the proper firmware is loaded on the devices, and so the devices are behaving as expected and not some other behavior. And this is exactly why I was talking about the need to standardize when this event happens, identifying it versus everything stops working. So with that, Lee, you want to add anything?
Yeah, so to add on to that, I guess we touched on some of it in the slides above, but to kind of, to Ross's point, when we talk about secure boot, that's kind of it's what we call, another term might be called measured boot. And people say that as soon as the power is turned on, it can be compromised. And so how can you go from powered off to fully booted and the system is running in a manner that ensures that nothing in that chain of events, from the bootloader to the firmware to the OS loader to the OS itself, nothing in that process has been compromised. And so we take and we do this, and this is the BIOS. This is the firmware for the storage controller. This is the firmware for the GPU. Any device inside the server that has firmware in it needs to be able to go through this process where that hardware root of trust of that device is such that the bootloader is hardened, say, maybe even in ROM. Then from that bootloader, the bootloader measures the next chunk of firmware through cryptographically secure methods such that that firmware is signed in such a way that that bootloader can then attest to that firmware is the firmware that it belongs there, and then on so forth and so forth on up. And as part of that, you can see where, say, we're actually pulling that off into a centralized hardened ASIC chip that we call Cerberus that does all that, making sure that as those devices get powered on, the firmware on there is the firmware that we expect and not something that's been tampered with in any way. So now on that, there are other areas of investigation. I think that, with the ideas we see these persistent threat actors and things like that going forward, where we actually want to be able to, even deeper than the CPU hardened root of trust, how do we ensure that the supply chain has been hardened such that nobody slipped in components during the manufacture or after, during shipping and that sort of thing, where those devices aren't the devices that we expect. And so we're working through some of those processes now as we go. So, and with that, next question.
Oh, and we've got a few of them. We've got some very attentive people here. So a couple more security ones, and then we'll move on to the form factor questions, there's a few of them. And then we're going to go into NVMe as a protocol for the future. Sound fair?
Yep. Yeah, you're loading us up here.
Hey, look, you're definitely going to get your nickel's worth today. All right. So with regards to all the issues that we're talking about, now Lee, you had mentioned earlier about doing encryption, effectively double encryption. So with regards to this, and for the sake of the secure boot issue, what kind of performance penalty does that have, and what kind it becomes no longer acceptable? I mean, at some point in time, the performance becomes, that trade-off has to be met. So how do you measure where that trade-off becomes acceptable or not acceptable?
Yeah, great question. So basically with that two-layer encryption, we're doing both software encryption and the CPU, and that hardware encryption, the self-encrypting drive encryption in the device itself. Now, software encryption, the idea is that the VM is actually in control of doing that encryption itself. So it has its own keys. We don't know anything about the key. It's done inside the VM, and so once it's passed out, it's unreadable by the host or any other piece of software in the software stack. It then goes down through the storage stack. It goes onto the device. The device has been provisioned with keys, or maybe multiple keys, maybe a single key, depending on the context. And then it uses its own AES accelerators and that sort of thing to encrypt that data as it stores it out onto the flash. And the nice thing about the idea of the hardware encryption, the SAD encryption in the device itself, is the manufacturers, they kind of know how fast they can write stuff to their NAND back end. And so with that, they can take, and their controller can be designed to ensure that they're going to be able to meet that bandwidth in the encryption pipeline. So that overhead is actually really minimal because they designed for their back end to ensure that balance is there and it doesn't get slowed down by that encryption process.
That makes perfect sense. And to that end, around the same time, a question came in about, and you're probably going to have to do a little definition of terms here as well. So the question came in this process with regards to how this is all working, where does zipline fit into it? And does Microsoft expect to default to zipline at both ends? And now the question is kind of slightly orthogonal to the purpose here, and it may go a little bit too deep into a specific implementation for Microsoft. And if it winds up being too specific, we can go ahead and bypass it. But I think it does probably wind up having a moment's worth of identifying what zipline means and where it fits into the big picture.
Yeah, so you think of this, so to define zipline for people who don't know, zipline is a compression implementation that Microsoft put together. I believe it's based on 9. That's basically we put and made into our RTL and into an ASIC. And with that, we took that RTL and actually open sourced it and gave that to OCP, such as other people can take that and do their own ASIC implementations or FPGA. Well, probably a little bit too beefy for an FPGA, but do their own ASICs to do basically bump in the wire compression of data as it goes by. And so you can think of these things around. I don't know how to talk about accelerators in general or these things in specific, but you could think of having the ability to set a series of acceleration engines, things that are doing deduplication, things that are doing compression, things that are doing encryption, as I said before, and on and so forth. And at the end of the day, you can think of some of these things where we may want to deduplicate the data, compress the data, encrypt it, and erasure or code it. And then it goes down to the drive in a replicated manner to ensure that there's robustness of the storage underneath. And so these are all kind of parts of the pipeline to get the data to and from the storage device and back.
Thanks. And covering that in a minute was well done. I'm impressed. And that was not an easy one to throw at you. I'm very impressed. So we've got so Ross, you're up. This is I'm giving you a heads up that you're next on the roadmap. So the question is actually for both Microsoft and Facebook, but I think Ross has been too quiet, so I'm going to go ahead and give it to him. In your mind, what do you think are the top 5 biggest pain points in using NVMe SSDs since the inception and adoption of the protocol? Now, this guy, this person has, phrased in such a way that we could probably spend, a master's thesis on this. But just in general, I mean, if you take in the top 5, just in general, what kind of pain points do you think are important since we started moving into NVMe?
So initially, when NVMe came out, there were issues with getting standard drivers. That has all been resolved, so it's all plug and play right now. And then that was the biggest challenge to start off with, I'd have to say. I mean, what's nice about NVMe is it's PCI based. So you have all your PCI lanes, and you can scale performance based on the number of lanes you have. And as you go from Gen 3 PCIe to Gen 4 PCIe to Gen 5 PCIe, you leverage all the benefits of that going forward. So NVMe has been around for quite a while, so it's much more mature than in the Wild West early days.
And Lee, you want to handle that, because there's some questions coming up with Denali that this would segue into. So.
Oh, okay. So some of the pain points with NVMe. Let's see. Obviously, yeah, as Ross was saying, early days, the drivers weren't fully baked and fully standardized. One of the things on that front was in the old days of SCSI and SATA, Windows would often take third-party drivers into an inbox in Windows itself, such that they would run with different chipsets, that sort of thing. NVMe is because it was a new standard and it was a pretty clean and standard across PCIe. We actually held the line on that. We said no third-party NVMe drivers in inbox in Windows. And with that, I think we were able to kind of pull the industry into a standardized direction that I think helped the industry overall. Other pain points, obviously, we talked through some of them around security and that sort of thing. But some of the things, pain points that we see, not necessarily, I'm going to say they're NVMe issues, but they're flash issues at scale, things where if it's going to fail in the data center, and it's going to fail in strange and spectacular ways. As I talked about the issue with the vias that we had with one batch of SSDs from a certain PCB maker. Other things around, hey, as things happen inside the SSD, firmware panics have a tendency to lock devices up or have them drop off the bus, and we don't know what happened, and so we have to go and do investigations and that sort of thing. Things specific to NVMe. I think right now there's kind of and Jay, you know this well, there's kind of a tension here where we wanted NVMe to be as simple as possible, but only as complex as needed. And there's kind of that tension where people come in, they want to add some stuff to it because it's been wildly successful. And so around that, it's like, okay, is something really of broad interest to the industry that it should go into the spec, or should that kind of be off in some sort of procurement doc or something like that? So I think that's one of the issues with success that we are now dealing with in NVMe.
Okay. Well, to that end, let's kind of do a quick kind of shuffle to the left and talk about the form factors a little bit. So, Ross, I think this one probably is right up your alley. There's actually, I'm going to combine 2 questions in particular. So, regarding the E1.L form factor, is it too big for a failure domain in a single node? And what's wrong with U.2 as a form factor? Because we talk about M.2 but not U.2. How does that fit into the decision-making process?
That's a great question. So let me start off with E1L. Me and Lee will have different answers due to different use cases. For me, I cannot put compute and E1L together, and I want a unified form factor that I can use for storage and compute. So for me, E1L does not work, but if you want the highest density form factor solution, E1L is the answer. Then let's talk about U.2 and E1S and M.2. They're all kind of wrapped around the same kind of topics. E1S is the direction we're headed. If you look at U.2 versus E1S from a performance point of view, you're very similar. However, E1S, U.2 has been around a long time. E1S was architected for the connector to work for Gen 5 PCIe, so it worked very nicely. It also has all the serviceability. You can nicely plug it into the front and hot plug it. It has a latch. It has an indicator for failure. It has excellent thermals. And so EDSF was born out of the need of we have problems and how do we come up with solutions. And that's how we've arrived in the E1S camp. Lee, do you want to tack anything onto this?
Okay. My turn, yay. We are actually more bullish on E1.L. As I say, we actually have our F2010 JBOF that we put 16 of these things in that JBOF and then have PCI switch in there that then attaches to the controller node. And so around that, some people, they talked a little bit about, I believe in the question they were kind of asking more, it's like, oh, what's the blast radius around that? And that's kind of, as I go back to that rot in place concept, these are one of the things we want to explore. I mean, obviously at, say, 16 terabytes or 32 terabytes on a ruler, the ability for, if that device dies, we have multiple replication, either through multi-column erasure encoding or three-way mirroring, so that if a device goes offline, we still have redundancy and we can rebuild that data as we go. That being said, obviously blast radius reduction is quite interesting, and that's where that rot in place comes in. Is as an industry, can we start to look at things where, oh yeah, I lost a die on that device. Give the OS indication of that. We can basically maybe take that thing, reformat it, and have it come back at a smaller capacity. Things like that, or a channel goes offline, or things like that. And so the idea is that instead of the device just dying as a whole, how can we kind of have this more graceful loss of capacity over time? And so ZNS is actually a really great answer to that, because ZNS builds in the concept of graceful capacity loss over time as the device wears. So.
Well, I think one of the things that's coming out of this particular conversation is that there's a bit of an interest in the form factor question. By the way, just so that people know, we at NVMe have written a white paper on form factors that is useful to know, and NVMExpress.org has that particular white paper available in their document section. So if you're interested in some of the conversations surrounding form factors, there's a pretty decent white paper. If I do say so myself, of course, I co-wrote it, so I have a little bit of a bias. With that, we are at the top of the hour, and I need to, unfortunately, close things off. If you've got additional questions, please get them in as quickly as you can, because we will be putting them into the Q&A blog, because there's a lot of really good ones in there, including some ones that I had wanted to hear the answers to myself. So please write in the questions, and by all means, do not forget to leave feedback for myself as well as for the speakers. A lot of work and effort has gone into these presentations, and we really appreciate your feedback to make sure if we've got something that we've hit or missed, and then good things we can continue, bad things that we could probably improve upon. So don't forget to leave feedback for us. Don't forget, we will be providing a Q&A to these questions that we were not able to get to. There's quite a few of them. And we're going to be posting that to the SNIA NSF blog at sniansfblog.org. And obviously, you can either download the attachments for this presentation right here, right now, or you can get it from the SNIA.org webcasts page, which is listed up on the screen. For more information about additional webinars, please follow us on Twitter at SNIA NSF, and we will be having additional webinars coming up, including everything from storage security to NVMe over fabrics, to the new transports, to everything you can imagine with regards to storage networking. So I want to thank our speakers. Thank you guys so much for taking the time to put this together for SNIA. This obviously has a lot of interest from a lot of people, and we're very happy that you were able to make it. Thank you so much.
Been a pleasure.
Thank you very much for having us today.
And
it's very kind of you.
It's very kind of you to join us. So for those of you on the call, thank you for taking an hour out of your day. I hope that you have a fantastic day, and we look forward to seeing you on future webinars for SNIA. Thank you so much. Take care.